For this video, we have two matrices which are 3 by 3 square matrix. And here we are going to solve for the basis of the range and the rank of the two matrices here under the linear transformation. The basis of the range is equal to the column space of the matrix. The column space meaning after you're done coming up with the reduced row echelon form of your matrix, those pivot columns or the columns with leading ones are part of your column space, and refer it to your original matrix so that you could get the columns or the vectors represented by the columns. So let's start with this first matrix here. By the way, I forgot, rank at the same time is the dimension of the basis of the range. We really need to get the basis first before we can say or we can determine the rank. Now, to start with this first matrix here, we are going to come up with the reduced row echelon form of this. To do that, of course, you could always multiply 1/2 to the row 1 so that you could make it a leading one. But of course, you will be dealing with fractions as you go on. What I would suggest here is to interchange row 1 and row 2 so that you will have 1, 1, 0, 2, 1, 3, 0, 1, negative 3 here. Notice that we already have a leading 1. Since this is already 0, what we need to do here is to only make 2 be equal to 0 by multiplying negative 2 to row 1 plus row 2 for a new row 2. So we have here 1, 1, 0, and then negative 2 times 1 is negative 2 plus 2, 0. Okay? Negative 2 times 1 is negative 2 plus 1, negative 1. Negative 2 times 0 is 0. So we have here 3. The next, you will also have here 0, 1, and negative 3. Now notice here that our second and third rows are actually multiples of the other. What does this tell us? Take note that if we are dealing with matrix with rows that are multiple of the other, we are expecting rows of 0 at the end. In short, one of which will become one row will become rows of 0. Let's show it further by, of course, start with this. Let's make this a leading one. You can multiply negative 1 to row 2 for a new row 2 so that you will have a leading 1 here. So 1, 1, 0. You have 1, 0 rather, 1, and then you have here 3. Also have, rather, negative 3. 0, 1, negative 3. When you are going to make this 0, this is what will happen. Negative of row 2 plus row 3 for row 3. So you will have 1, 1, 0, 0, 1, negative 3. Then negative of this plus that, that's 0. Negative of negative 3 is positive plus this 0. See, we have here row of 0 because we have rows that are multiple of the other a little earlier. Okay. Now what we could do here is to since this you don't need to come to make this 0 or 1 because we already have leading 1 here. What we need to do here is to make this 0 so that we will have a reduced row echelon form, because in the meantime as of this matrix is concerned, we still have, or this is still in its row echelon form. So we can make this 1 by multiplying negative 1 to row 2 plus row 1 for a new row 1. Hence, you will have here 0, 0, 0. This is still 0, 1, negative 3. Negative of 0 is still that, 1. So negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times 1 is positive 3 plus 0. You have positive 3. So this is now the complete reduced row echelon form of our first matrix. Now, we need to examine here which columns contain leading 1. We have this column here and this column. These two are considered to be pivot columns because these are the columns that contain leading ones. And if we're going to refer this to our original or initial matrix, the first column and the second column is part of your column space. Column space is equal to the basis for the range. Hence, your 2, 1, 0, this first column, and the second column of 1, 1, 1 will be part of your basis. So we have here the basis for the range of t. So you have, again, the first column and second column. So you have the column of 2, 1, 0, and the 1, 1, and then 1. Or you could write it like this: 2, 1, 0, and then 1, 1, and 1. Okay? Now let's proceed to the rank of t, as this is equal to the dimension of the basis of your range. In short, we're just going to look at the number of vectors that are part of the basis of your range. And since we have 2, your rank of t is also 2. So this is how we start solving for the basis of the range and the rank of t, or of our first matrix. Let's duplicate the same process. By the way, before we duplicate the same process, take note that the basis of the range here is just one of the possible bases. We can also use here the concept of the row space to come up with the basis for the range. But since we use here the column space, and we also used the column space in our previous examples, let's do the same thing here. So matrix A here as well, you will have to come up with the reduced row echelon form. So this is already a leading one. Let's make this 0 by multiplying -1 to row 1 plus row 2 for a new row 2. No need to manipulate that because it's already 0. 1, 1, -1. So -1 times 1 is -1 plus 1, 0. -1 times 1 is -1 plus 2, that's 1. -1 times -1 is +1 plus 1, 2. You have 0, 1, 0. Next, this is already a leading 1. Let's make this 0 by multiplying -1 to row 2. Sorry, that's plus, my bad, plus row 3 for a new row 3 to make this 0 again. So you'll have here 1, 1, -1, 0, 1, 2, 0. Let's do this. -1 times 1, -1 plus 1, 0. -1 times 2 is -2 plus 0. You have -2. Okay. Unlike earlier where we already have rows of 0 here, we still have a row here which has an entry. In short, we are going to multiply this by a certain negative number, okay, or -1/2 of our row 3, okay, so that this will become 1. So you have here 1, 1, -1, 0, 1, 2, 0, 0, and then we have -2 times -1/2, that's 1. Okay, this is still the row echelon form. We need to make these entries 0 as well as this, because the reduced row echelon form means that the columns with leading 1 should have other entries, should have no other entries aside from 0. So let's make this 0 by multiplying -2 to row 3 plus row 2 for a new row 2. Then we simply add row 3 plus row 1, sorry, that's 1, so this will be 0, okay, to have a new row 1. So we'll have here 0, 0, 1. This is 0, 1, and 2. This is still 1 here. So -2 times this, row 3, sorry. -2 times this is, sorry, I forgot, this is what I meant. So let's start. -2 times 1 is -2 plus 2, that's 0. Then add row 3 plus row 1, so that's 1 plus -1, that's 0. Here, this is still 1 here. So to make this final 0, you will have negative of row 2 plus row 1, that's 1, sorry. Row 1 for a new row 1. Okay? 0, 0, 1, 0, 1, 0. So you have 1 here as well. -2 times 1 is -1 plus 1, 0. This is still 1. So we are done with the reduced row echelon form of our second matrix. And here we can see that all columns contain leading 1s. In short, all columns of our initial matrix are part of our column space, and they are part of the basis for the range of T. In short, for the basis for range of T, is a set containing 3 columns. The first column is 1, 1, 0, then 1, 2, 1, 1, 1, 0, 1, 2, 1, and then negative 1, 1, and 0. Let me review. Here you have 1, 1, 0, 1, 2, 1, negative 1, 1, and 0. Or you can write it like this: 1, 1, 0, 1, 2, 1, and then you have, sorry, this is negative 1. Negative 1, 1, and 0. This would mean that the rank of t, here being that the dimension of the basis of the range, is 3, since we have here 3 elements, 3 vectors, 3 columns for a column space, so the rank of t is 3. So this is how we show the range, or the basis for the range or the rank of the linear transformation defined by these two 3 by 3 matrices. Thank you very much for watching.